Yes,
So,
we start now.
okay. So today we will solve together a problem related to chapter 3. We will see also how to use the thermodynamic tables to determine the state at any point, which will help us into calculating the efficiency of a cycle and to determine each part of the cycle for what purpose it is. So to start with, before going over cycles, we will start by problems, doing analysis on just one part, okay? And after these problems, this introductory problem, we will take into consideration cycles. So we will see several types of cycles. Some cycles are used, for example, to cool or to heat a space. Then in this case, we will provide electricity in order to heat to a refrigeration system in order to heat or cool. Other systems just want to produce electricity. So in this case, we will ensure a source of heat, and from this source of heat, we can convert heat to work. So depending on the purpose, the transformation of energy will completely change. So sometimes we transform electrical energy to heat energy, or in the other cases, we transform heat to electricity. So before starting with cycles, as I said, we will go a little bit over several components that we might find in cycles and see what are their functions. So to start with, we will do a problem on a nozzle. We have a steam at zero point 0.6 megapascal and 200 degrees enters an insulated nozzle with a velocity of 50 meters per second. It leaves at a pressure of 0.15 megapascal and a velocity of 600 meters per second. Determine the final temperature if the steam is superheated in the final state and the quality if it is saturated. Okay, so let me zoom it a little bit for you. Okay, so here, always the first step in a problem, try to know what are the inputs and what outputs should I find. Okay, so first, they gave us conditions about the initial state. So we know that at the inlet of the nozzle, we have a velocity of 50 meters per second, a pressure of zero point 0.6 megapascal, and a temperature of 200 degrees. So the inlet state is completely defined. Okay, so here we know everything about the inlet, and we will see together that if we know just two properties, we can find all others. Yani we can find the enthalpy, the entropy, whatever is needed for our analysis. Okay. Now, at the exit conditions, we know also the exit velocity and the exit pressure, but we need maybe we need other information to if you want to be able, because at a certain point to know all information, I need to know two properties at least. Okay, so here what they asked, what they told me is that the steam is leaving, so it's leaving at a pressure of 0.15 megapascal. What I want to find, I should find the final temperature. Okay, so they are asking me what is the final temperature of the steam. So as I told you, always think in your mind that if I want to completely define a state, I need two properties. The first property is given, which is the pressure. I will try to find another property, and this other property needs an equation. In general, whenever you have a certain control volume, and you have inlets and outlets, try to always write your energy equation, because your energy equation will give you a certain unknown. Okay, so if I go a little bit back to the course material to remind you about the equations we derived in the course material. So here you can see, for example, in general, we work in steady state processes. Okay, so in the course material, we have derived first here, we derived the energy equation for general case where we can have transient conditions. Okay, but in general, in processes involved in cycles, we deal with steady state conditions. And in steady state conditions, the derivative with respect to time is zero. Okay, so this equation will give me the energy equation in a steady state condition for the case of one inlet, one outlet. So if I have just one inlet, one outlet, I said this is equal to zero. Okay, and then I can solve for, at least if I replace in my equation, I can solve for a certain unknown. So if I have just one unknown in my equation, I can find it. In the majority of cases, for example, I know the conditions, all conditions at inlet, and at outlet, for example, one of the conditions is unknown. For example, if the enthalpy is unknown, I can find it from the energy equation. Okay. If you have several inlets and several outlets, all you have to do is just to add sum of sum of m times this term at inlet and sum of m dot times this term at outlet. Okay, and if one inlet, one outlet, so you just have one term at inlet and one term at outlet. So the most used equation, especially in cycles, is this one. It is the steady state equation with one inlet and one outlet, okay, which is this one. So it is the most one used, but of course, you should know that if I have several inlets, just I should do the summation at inlets, and here I will do summation at outlets, okay? So now we will try to apply this relation for the nozzle, okay? Now, first, I should understand what is the function of the nozzle. So if I go back to my problem, okay. First, in general, the purpose of nozzle is to change the velocity by changing the cross section. So as you can see here, the cross-sectional area is varied through the nozzle. This will allow me to increase my velocity because I entered at a velocity of 50 meters per second, and at exit I have 600 meters per second. On the other hand, the pressure is decreased, okay, from 0.6 megapascal to 0.15 megapascal, okay. And they told me a very important information, that my nozzle is insulated. My nozzle is insulated. This means what? This will help me to simplify which term? When I have good insulation, do I have heat transfer with ambient
Q dot,
conditions,
right?
with the
Q,
surrounding?
the
Heat
Q will be
transfer.
So when they say
Q dot.
insulated nozzle, then I can simplify the term, the heat term can be simplified. And is my nozzle producing a work, or do I provide work to my nozzle?
no.
No. So no heat, no
No.
work. So these two terms will cancel out in my expression. Okay? I just have change in velocity, which should be taken into consideration in the equation. So going back to my equation here, I can say that no heat, so the first term is cancelled out. I know that in steady state application, m dot n equals to m dot out. So after saying that no work also, since m dot n equal m dot out from continuity equation in steady state conditions, this means that the inlet flow rate is equal to the exit flow rate. M dot can be simplified also from both terms. So I end up with the following. I end up with, at the initial state, at the inlet state, H inlet plus V inlet square over 2 plus G Z inlet equals to H exit plus VE square over 2 plus GZ exit. Now, when they don't give me information about elevation, this means that or I have negligible change in elevation, or I have motion in a horizontal plane, so no change in elevation. This is why I can say that no change in elevation, and I cancel out GZ inlet equals to GZ outlet. So I end up only here for the nozzle. The energy equation is much simplified. I have H at inlet plus V inlet square over 2 equals to H at outlet plus V outlet square over 2. Okay? And if I go back to my problem, I have H inlet given, I have V inlet given, also V exit is given. The only unknown in my equation will be H at outlet. So now from energy equation, I can determine the exit enthalpy. And once I know it, I know also another property, which is the pressure. As I told you, once you know two properties, you can get any other property. So you will be able now to determine what will be your temperature. So if we go back to the problem, let us write the energy equation. So from energy equation, I have H inlet plus V inlet square over 2 equals to H outlet plus V exit square over 2. But remember that H inlet is not directly given, okay? They gave us information about the inlet state. From this information, I will get at H at inlet, okay? So let us check how to get H at inlet. At inlet state, what do I know? I know these two properties, the pressure and the temperature. Okay. Now, what do I know also? I know that I am dealing with steam, okay, which is water in the vapor. So it's I have here water in vapor state. Okay. Now we will learn together how, knowing these properties, we can get H at M. Okay. To do this, we need the table. We need the thermodynamic tables. I sent you today the link for the thermodynamic book. And if you had already taken thermodynamics, maybe I don't know if this was your book or not, but for the tables, please go to the course, the Zoom recordings folder. In this folder, you have all links related to the course. So the last link is a WeTransfer link for the book. Okay, I will open now the book here. This is the book, Fundamental of Thermodynamics. You have the link. Please try to download it within 1 week. Try to download it today or tomorrow to not forget. Okay. So at the end of this book, you have an appendix containing all tables we need for the calculation of the properties of steam, of some refrigerants, of some gases. Okay. So here first, let me introduce you to the appendix. You have first appendix. The first appendix is for properties of ideal gas. So sometimes we'll use it. So we will use it in in one example. Okay. So in the first appendix here, for example, you have here properties, for example, of some solids, and you have here properties of ideal gas. Okay. So for example, we might use some ideal gases tables. So for instance, if you have the temperature and you treat a gas as ideal, you can get the enthalpy value. So this is a table that we will use in these problems. Table A.8. So just you need to know the inlet temperature, the temperature of this ideal gas. From the temperature, you can determine what is the internal energy, what is the enthalpy. Okay. So this table, we'll use it in one of the problems. This is for nitrogen here. It depends on the gas you have. If it's nitrogen, then you can use it. If you have CO2, for example, you have another table for CO2. So here for CO2 also, if you have the temperature, you can get the value of internal energy and enthalpy. You know that uh, in general, we can treat gases as ideal gas if they are in conditions close to ideal gases. Okay. So we have so in general, we will tell you in the example if you can treat it as ideal gas or not, because for some combination of pressure and temperatures, the behavior of the gas will not be close to ideal gas behavior. So we should specify for you in the problem if you want you to use it as ideal gas, or if we prefer, because also we have tables for CO2. So from the givens, I will tell you if you use ideal gas, if you treat it as ideal gas, or if you use its own tables. Okay. Now, Appendix B is mainly for water, and this is the most used one. We use it a lot because we are dealing with steam cycles in this chapter, and also we deal with refrigeration. So in some cases, I can use refrigeration, refrigerate some refrigerants different than water. So you can have, for example, R410 or R134. So we have several types of refrigerant, and each refrigerant will have its own tables. Okay, so here, in Appendix B first, the first set of tables is for water. Now we have several tables. We have what is called saturated water. When we talk about saturated water, this means that we have a mixture of vapor and liquid. Okay. In this case, you need to provide as entry, you need to determine that the temperature. Okay. So for example, you can have saturated water with temperature entry. You can have saturated water with pressure entry. What is the difference? So sometimes you know that you are in a saturated state. You know that you have a mixture. If they provide you with the temperature, then you will use the saturated water with temperature entry. If they provide you the pressure, then you will use the table of saturated water with pressure entry. Okay. Now, what is the pressure we give here? This is called, at a certain temperature, we have a saturated pressure. Okay. What is the meaning of it? The meaning of this pressure is that if I am to have a saturated condition, this means that I have mixture of liquid and vapor, the pressure should be constant. So when I deal with a saturated condition, okay, I have, if you have seen in the course material, I will have constant temperature and constant pressure, and then I will have a change of phase. So each temperature will have a corresponding saturated pressure. Now, if I am above the saturation pressure, who can tell me I will be in the liquid zone or in the vapor zone? So if I tell you I have water, I have water at temperature of 20
Liquid,
degrees.
compressed liquid,
Yeah,
right?
if I increase the pressure beyond 2.339, then I will be in compressed liquid zone. And if I have a pressure below 2.339, I will be in which state?
Yes, yes.
I will be in superheated state.
Superheated.
Okay, so from temperature and pressure you can know in which state you are. Okay, now whenever I am in a, so if I do a small representation for you, if you go to the graph, let's say you have this, and this is your it's like a bell shape like this. Okay, so these lines represent constant pressure. Okay, so here we call them isobars. So if I go, if I move under constant pressure and I vary the temperature, this zone is the compressed liquid state. Okay, so I have a certain pressure, but for low temperature, okay, I can. So if I fix the pressure at lower values of temperature, I have the compressed liquid state. Once I reach the saturated temperature corresponding to this pressure, then I will move in inside the belt. I have change of phase. So this point here will correspond to 100% liquid. This is this point is 100% liquid, and at this point, when I reach the temperature of saturation, I will start to have change of phase from liquid to solid. Okay, so this is 100% liquid. This state here is referred as saturated liquid. So this point here represents saturated liquid. Okay, now any point in between, you have mixture. So here you have mixture of phases, liquid and vapor. Okay, then to define your mixture, you need one property which is called the quality. Okay, and the quality X. The quality X is between 0 and 1. So it is called the quality. It represents the percentage of vapor into the mixture. Okay, so this represents the percentage. The quality is the percentage of vapor into the mixture. So when I am at this point, what will be X at this point? When I have 100% liquid, X is equal to what?
1.
No, 0. Exactly.
0.
Because when I have 100% liquid, this means that I have 0 vapor. And X is the percentage of vapor. So here at this point corresponds to equality of 0. X equals 0. And the other extreme point is this one. This is called the saturated vapor state. Okay, so when we talk about saturated vapor, then we are at this point. Okay, this point corresponds to 100% vapor. And at 100% vapor, I will have X equal to 1. Okay, and anywhere in between these 2 points, at any point, I will have X between 0 and 1. So at any point here, okay, X will be between 0 and 1. Now, why X is very important? Because if I know the value of X, I can determine the properties, all properties at this point. Okay, so for example, what they gave you here in this table, for example, here I have the specific volume in meter cube per kilogram. Let's say, okay, you know X. Let's say, for example, X equals 0.6. If you know the quality of the mixture, you can determine all properties. So for example, if X equals 0.6, you can say that the specific volume at this point will be equal to VF, which is the volumetric, the specific volume at saturated liquid, okay, plus you add to it 1 minus, you add to it X times VFG. I will tell you what is VFG. Okay, you have that VG is the state at saturated vapor. Okay, VFG is the difference. It represents the difference between them. So VFG is simply VG minus VF. Okay, VG minus VF. So if you know X, you can find the property by saying that I take the property at saturated liquid, I add to it X times the difference between VG and VF. Since this difference is widely used, yani instead I directly gave you the value. Yani VG minus VF is given by VFG. Okay, so you can directly replace this term by VFG. Okay, so numerical example, if I have 20 degrees and X is equal to 0.6 and I want to find V at this state, I just say at 20 degrees VF is 0.001002. I should add to it X times, so 0.6 times VG minus VF. And to verify that your formula works well, if X equal to 1, I should obtain what? I should obtain VG. So, and this is what will happen because I will have VF plus VG minus VF. VF will simplify and I will get the value VG. And for X equals 0, I will get just VF. Okay. Now, any question until here before I continue? Okay. Now, you have several properties of interest. You have the specific volume is as its name indicates, is the volume per unit mass. You have the internal energy also, but in general, in cycles, we use a lot other properties. We use a lot the enthalpy. So in general, even the specific volume also we can use it. We will see in examples how, especially for a pump. Okay, but the most useful tables for us are the one with enthalpy, because enthalpy is in the energy equation, and we use it to define the states at each point. Okay, so for example, in our example here, what do we know? We know that we have steam. So first, since it's steam, when they tell you steam, this is in vapor state. Okay. So when they say steam, it means that I am in the vapor state. So of course, because I am in the vapor state, this is a superheated state. Okay. I will not go and look at saturated tables, because saturated tables will include mixture of phases. Okay. So I should look at other tables, which are tables of steam. So these tables are called saturated vapor, uh, sorry, superheated tables. So I will go to and search for superheated tables, and in these tables I will put my inputs. So what do I know about the inlet state? I know both the pressure and temperature. So I will go to superheated tables and search for a pressure of 0.6 megapascal and a temperature of 200 degrees. What will be the value of enthalpy? Okay, so this is what we will do together. Let me go to the tables, and I will try to search for superheated tables. So I don't want saturated water. I continue down. This is also saturated water. I continue. Now, as I told you, you have also saturated water with pressure entry. So instead of giving the temperature as entries, I give the pressure as entry. So depending on the problem given, you will choose which table to use. Still saturated, still. Okay, this is superheated vapor water. This is what I want. Okay, now in superheated vapor water, they give you for different pressure. Okay, for different pressure uh, and variation of temperatures, what will be your properties? I want to have, I have in my problem, let us go back to the pressure. The pressure is 0.6 megapascal. So it's 600 kilopascal. Okay. Here I am already at 2000, so I should go up. It is before. The table of interest for me is before. I want to search for 600 kilopascal. It's not here. It's here. Okay. This is what I want. I want superheated state. So I have the steam at 600 kilopascal, and I can verify that I am in the state because look, they gave me a temperature of 200 degrees. Okay, 200 degrees is higher than the saturated temperature. What you can see here in brackets is the corresponding saturated temperature for a pressure of 600 kilopascal. So for a constant pressure, if I go higher than the saturated temperature, I will reach the superheated state. And my temperature of interest here is 200 degrees. Okay, so from here, I can, I am interested in the enthalpy. So I will look at my table here. Enthalpy is the third column. So, so I will take this value. Okay. The enthalpy is 2850 because this is the third column. Okay, so this is my value of interest. Okay, so I have calculated from tables, I have found what is H at inlet. Now, once I have H, I can go back to my equation. So here in the solution also, I provided you with the table to see how we did the selection. Okay, so you have here all details how you select the value of 2850.12. Once you find it, you can go back to your energy equation. And now I have H inlet, I replace it. Just please pay attention for units, okay? The thermodynamic tables will give you values of H in kilojoule per kilogram, okay? And you know that V square, what is the unit of V square? It's meter square per second square, okay? Meter square per second square, you know it's equivalent to which unit? It is joule per kilogram. Why? Why it's equivalent to this? Because look, going back to your equation, if you go to the energy equation here, in any equation, in any physical equation, I should have the same dimension for all my terms, okay? So here, when you add h to v square over 2 to gz, these three terms should have same unit, okay? Because it doesn't make sense to add terms that have different units, okay? Let us verify. We know that H is in joule per kilogram, but let us verify that joule per kilogram corresponds to a meter square per second square, okay? To verify this, you can just go back to the concepts. What is joule? Joule is energy, okay? And what is energy? Energy is, as dimension, is force times distance, okay? Why? Because you know energy unit is like work unit. And how to calculate work? Work is force times distance, okay? Now, what is the unit of force? Force is mass times acceleration. From Newton's second law, F equals sum of forces equal ma. So unit of force is mass, kilogram, times acceleration, and the acceleration unit is meter per second square, okay? And then I multiply by distance. Don't forget here to divide by kilogram because you have joule over kilogram. So times d, the unit of d is meter, so times meter, and then over kilogram. And now if you simplify, look, if I simplify, I have kilogram, here will be simplified, and I have a meter per second square times meter, it will give me meter square over second square. So as you can see here, units joule per kilogram correspond to meter square per second square. But my thermodynamic tables are not giving me H in joule per kilogram. It's giving me H in kilojoule per kilogram. So I can do one of two things. Or I convert H to joule per kilogram by multiplying the value of H by 1000. Or the other possibility, for V square over 2, if I use V in meter per second, I should divide my result by 1000. So don't forget this, because if you don't do this, you will get wrong results, okay? Now, concerning G times Z, here I don't have it, okay? But in case I have it, G is, in general, I can use it 10, okay? It's 10 meter per second square is the gravitational acceleration. And Z, I will use it in meter. Z should be in meter. Now, in case I am using H in kilojoule per kilogram, also GZ should be divided by 1000. Okay? Or if I want to keep it in meter, meter per second, meter square per second square, I should convert H to joule per kilogram. Okay? So it's up to you. Just make sure to have same units for the three terms. So here they decided to convert the velocity term. This is why what they did is that they divided here, after replacing V inlet by 50 meter per second, they divided the result V square over 2 by 1000 to get same units. Okay? And then V exit also is replaced by its value. I just have one unknown, which is H at exit. I get H at exit. Now, what was the question? The question was to know what is the quality at the exit of the nozzle. Okay, so now to find the quality, I can do it because I know now two properties. I know from calculation what is H at exit, and from the given, I have another condition that is given, which is the pressure. Okay, so if I go up, I know the pressure is 0.15 megapascal, and we said that to know the final state, we need another property. The other property was the enthalpy. So let us check. Look, they didn't even told us what is the final state. They said, determine the final temperature if the steam is superheated in the final state, and the quality if it is saturated. So here I have two possibilities at the exit. It might be in the superheated state, or it might be in the saturated state. To know, I should find the two values and then go to my tables to know in which state I am. I should open a new session to continue. Okay, so I will end this session because we have less than 1 minute. So let us open a new session to continue.